very much.
Thank you. I'm going to give you a brief introduction, an overview over what we've been doing with that code. I myself am a PhD student. I joined the team that currently consists of these 5 people plus my professor who are working with that code. I've not been working with it for too long, and so don't expect too many insights into the numerics, please. We use Prime to compute dispersed multiphase flows and fluid structure interaction. And it is an in-house code. It's been developed for 12 years by 3 to 4 people at a time, and who are working on development and application. We do lots of physical application, evaluation of physics using that code. These are some test cases to give you an idea of what the code can do. Dispersed multiphase flows are flows that feature a dispersed phase in a continuous phase. So these are often particles, deformable or not, spherical or ellipsoid, or bubbles of any shape. Many more are possible. This is one production case, one typical application. It's a sediment transport case with spheres being transported in a flow, and this was done by colleagues of mine. It's a fairly big simulation. It's scale resolving, features 1.4 billion cells. This makes data handling very challenging. We have 27,000 spheres, and it was computed on 8,000 cores approximately during 2 to 3 months. We can vary the shape, which is important here. It has an impact on the dunes that we see in the simulations. And we can also have bubbles without a predefined shape. And this is relevant in flotation cases, for example. Bubble columns are used in liquid metal to clean the metal, and so this is a case relevant for industrial applications too. And this is a smaller simulation, also scale resolving though. I'm going to briefly present the code. So when thinking of how to solve this, the first idea I would have is to sort of construct the mesh around the particle and to move it with the particle. This is an interface tracking approach. It's possible, but it's very tedious because the mesh obviously has to be regenerated as the particle moves, and thus makes the method computationally expensive. It is also tricky in combination with structured grids, and especially since the collision of particles or bubbles changes the topology of the entire problem. We have chosen a different approach. We use the Immersed-Boundary-Method, and the Immersed-Boundary-Method is very efficient because we solve the fluid PDEs on a constant regular background grid. And we can use standard solvers here. For the dispersed objects, such as the particle, we solve many ordinary differential equations. And the coupling is done via a distributed force along the surface of the particle. So we put many Lagrangian markers on the surface of the particle, and within the solution routine, it is made sure that the velocity of those markers corresponds to the velocity in the fluid field at the same positions, and this is done by computing the force that is necessary to correct the fluid velocity field, and this force, this IBM force, is then introduced into the fluid field. This method can easily be extended to handle many different dispersed objects. And we have implemented spheres, ellipsoids, bubbles, flexible structures, and rigid bodies of arbitrary shape. And this entire approach has the advantage that we can freely choose any solver for either problem. So we can use efficient solvers for the fluid and efficient solvers for the particular kind of disperse objects we have. All we have to do is provide the communication between the two solvers. So how do we use PETSI? We need massive parallelization, and that's where we use PETSI for domain decomposition. We usually decompose our domain into cubish-like subdomains. We do ghost cell communications using PETSI calls. We currently only use hypersolvers, but these two are provided by PETSI, so that is an advantage of using PETSI. And we do parallel file writing and reading with using PETSI. The solid phases are, however, handled using pure MPI calls at this point. Let's have a look into the solution routine for the fluid. It's a 3-step Runge-Kutta scheme. For each one of the solution steps in one time step, we solve an explicit Runge-Kutta equation. Well, we solve an explicit Runge-Kutta step. And this is hand-coded. It's explicit, so it's not very difficult to do. We then solve the equation of motion for the solid. There we use third-party solvers or our own solvers, depending on which dispersed element we're looking at. We then have two more equations that have to be solved for the fluid, one in Helmholtz kind and another one in Poisson kind, to correct the intermediate velocity field. And this is done using hypersolvers. We have tried different solvers, and our default right now is to use the struct BCG and the big step. Okay, parallel in-out is easy. All we have to use is the PETSI, the vec_view command, having set up the PETSI view before, and this would be a lot harder to do by hand. In the end, we end up with a very parallelly efficient solver. This is a case similar to the video I've shown a few slides before. And here we have up to 8,000 cores, and it doesn't speed up perfectly, but it's not too bad. We do have some bottlenecks that we're working on, so this is to give perspectives. The interpolation that takes place in the region of the surface between the background grid and the Lagrangian markers can raise a performance gap if we have too many Lagrangian markers. So our question here is if this can be done more efficiently. All this interpolation is hand-coded using MPI calls to get the data, and it's then interpolated. We currently only employ uniform grids. Our problems oftentimes are non-uniform though. If we think of the sediment transport problem, and if we imagine the channel to be sufficiently high, we can save computational time by having fewer grid points in the upper part of the channel. This is currently not possible, but this is something we would very much like to do. Our minimum block size, that is how many cells a single core gets to compute, is currently limited by the way we have implemented the disperse phase handling. Right now, if the center of mass of a particle is in a subdomain corresponding to one core, that core gets to do the master computation for that particle. That core solves the equation of motion, but that core also has to communicate with the surrounding, the core is corresponding to the surrounding subdomains to exchange data, fluid data and also particle data. And this is currently only implemented for a 3x3x3 core box. Could be extended to more cores, but here too, the question is if this can be generalized using Patsy methods. So this is the last slide of bottlenecks. We have 15 combinations of solid phase collisions. Collisions are a very tedious task to program, and we currently cannot we don't have all these combinations implemented. So this is something to work on, to have the ability to compute multiple different disperse objects at the same time. And data storage is a limiting factor. We have huge binary files, and to do much post-processing, it would be sometimes good to have a way of storing compressed files that can also be lossy. And so to our current knowledge, and that was before I came to this meeting, we were using hypersolvers because to our knowledge, Patsy solvers are insufficient. Maybe that's not the case. We'll have to look into this. And if there is a post-processing toolkit that can read the Patsy binary files that we write directly, that's something we'd be interested in. Otherwise, I think we should shift our output to use standard HDF5 files. I'd like to finish up the talk with a few more cases of applications. Here we have flexible structures in a channel featuring a phenomenon called Monami. This is an instability we see in seagrass, for example. A similar case can be observed in cornfields. And this too is a fairly big simulation. It is scale resolving using LES subgrid scale modeling. 700 million cells was computed on 1,000 cores. And for each one of those blades, a beam equation is solved, Khosrow beam equation. We can do we can incorporate more physics, magnetic fields, for example, which can have an impact on the way bubbles rise. And we have simulated temperature before. So this is it. Thank you very much for attention.
Thank you, Bastian. Any questions out there in the audience? Matt.
So, you might buy a little bit. What is that hypersolver
We use the PCG solver for the Helmholtz equation problem we have. Fun?
What is the precondition? If precondition conjugate rate, what is the precondition?
I'll have to look it up on my laptop. I don't know it. I don't have it memorized.
Oh, that's what it is. Okay. Yeah, I think we could probably replicate that. Since you're on a structured grid, you could probably replicate what they're doing by just setting up the PCMD. Because you don't need probably the same. We can talk about it.
I'll get back to you after in a break, maybe. Cool.
Yes.
Make comments, maybe suggestions or ideas. With your I/O, ZFP might be interesting for you.
ZFP.
ZFP, floating point compression. Maybe try Adios instead of HDF5 because it's built into it as well.
Huh.
If you want to avoid post-processing, you could probably, your grid is very simple. You could instrument it up as a hardware catalyst and do live in situ processing. So you wouldn't even put the data on disk, just generate your images immediately.
So you said that you need these long runs to converge statistics, right? What are the kind of statistics that you're trying to get out of the post-processing?
Oftentimes it's just time averaged velocities, but we have cases where the time scales over which statistics for particles converge are much longer than those for the fluid. So this too can slow down the entire process.
If there are further questions, maybe we should take them at the break. Let's thank Bastian one more time, and if David could come up.